If you want to support multiple languages in your graphical user interface, set your character set to Unicode in your Visual Studio property page. Unicode supports a vast array of character sets. To render text, I use the free Type Graphics library, commonly known as FTGL. It's a library used to render text with OpenGL. You can build the libraries of FTGL in a separate application, or you may be able to find them pre-built online. To support this library in our application, we include the FTGL source and FreeType include folders as additional directories under the C++ general configuration properties. Next, we make sure that our project is set up to include the folder that the FTGL libraries reside in. You do this by adding the folder to the Additional Library Directories section under the Linkers configuration properties in Visual Studio. To ensure that the FTGL static and FreeType libraries that are statically linked to our executable at build time, we add the .lib files to the Additional Dependencies section under the Linker input property. We must also add FTGL library static to the preprocessor definition section of the C++ configuration property. Once this is done, we need only to include the FTGL header file wherever we will need the library's modules. The text class is friended by the GUI text box and OpenGL class, so they can access its private members. The font path string indicates where on the drive the font resides. The string array holds character strings for multiple lines of text. The bounding box indicates the area that each string occupies. The position indicates the original location of the string. The adjusted position indicates the position of the string after it has undergone left, center, or right justification and is the actual rendering position. The color and shadow color members indicate the foreground and shadow color of the text. The FT texture font class is a derivation of the FT font class and can handle texture-mapped fonts. The justify enumeration indicates whether the text is aligned to the left, center, or right of its parent. The visible boolean determines whether the text will be rendered or not. The static boolean indicates whether the text will need to be updated after creation. The constructor calls the create function. The create function first prepends the font folder name, then appends the font file type to the name of the font that was passed through. To allow the font size to scale with the resolution of the screen, we calculate the scale of the text by dividing the passed-in size by the reference size, which is 40. We multiply this result by the scale of the current screen resolution. The screen_scale function also uses a reference size for its X resolution, which is 1024 pixels. We retrieve a pointer to the font using the getFont function of the font manager. If we fail to receive a valid pointer, it is likely that the font does not reside at the path specified. So we then check in the system font path, which is the fonts folder on the Windows operating system. If we fail to find the font there as well, we return false. If we have no problem finding the font, we set the member variables and check for whether this text is static. If it is, we set the string and the adjusted position based on the extents of the bounding box. If the text is not static, it means we want text that will be dynamically updated, such as a timer for the HUD. The setJustification function positions the text based on the justification style that was requested. It comes in 3 versions. The first just sets the enumeration value of the justification. The second sets the enumeration value and adjusts the text by it. The third sets the justification via a string argument. The setArguments function uses a variable argument list to add arbitrary values to the string, such as other strings and numerical values. The _s version of vsprintf function prevents memory overwrites in the Windows operating system by defining a maximum buffer size. The render function draws the text using the graphic library's drawText function. In preparation for writing to the color buffer, we copy the current color information by calling GL push attribute. We disable lighting because it can interfere with any alpha blending the text needs. We then use the render function of FT font to add the text to the draw command buffer. We add the shadow text to the command buffer first so that the foreground text is rendered over it. We offset the shadow text by the shadow offset value multiplied by the screen's X scale to keep the offset in proportion to the resolution. Set Font to Size gets a new font from the font manager that is of the requested size. Font Manager encapsulates a hash map of pointers to text your font's reference via a string that concatenates the font's path and size. The getFont function appends the size of the font to its path. It then checks if the font is already in the hash map. If it is, it returns a pointer to it. If it is not, it creates a new font with the path as the parameter for its constructor. We delete the font and return null if there is an error in its construction, or the size we want is not supported, or Unicode encoding is not supported for this font. If there are no problems, we create a new entry in the hash map and return the pointer. The destructor iterates through the hash map and deletes all the allocated fonts. The language strings class holds an ID to identify the language strings and an array of strings, each of which is for a different language. Here is an example of a language string structure in the language strings configuration file. As you can see, the strings can be different lengths and size, which means you might need to have separate GUI string configurations based on each language, as I do. The String Manager class derives from the Singleton class because we only want one instance of it. It also derives from the Parser class, so we can load in the language strings file. It holds a map that uses the language string's ID as a key and a pointer to the language string as the value. The strings tokens array holds the tokens that will be used to read in the language strings. In the initialize function, you can see the tokens initialized for the ID and the 7 languages that are supported. The readData function appends the file name to the string representing the folder that the language strings file resides in. If we fail to open the file, we create a default version and open that instead. The parse structure then reads in the structure, during which it calls the createStructure class to instantiate the language strings. The createStructure function checks if the language string ID is already in the map. If it is, we have used the same ID at least twice, and we need to correct this. Otherwise, it dynamically allocates a new language strings instance and sets the language string for each language. We then add the language strings as a new element of the map. The getString function copies the string ID to a character buffer and checks for any errors in the process. If all goes well, it searches for the entry in the map and returns the string in the current language. Otherwise, it returns null. The free memory function iterates through the language strings map and deletes all the language strings.